Hello and welcome to your asynchronous day on some more stuff related to carbon modeling and understanding the carbon cycle. Now, if you're in period 2, I don't believe that we've gotten to these notes today yet. So if you are in period 2, there's a separate video I'm going to be putting in the email related to the information regarding the greenhouse gas effect, how CO2 values are going up, and also how that impacts heat distribution with surfaces of the Earth. So today we're going to briefly talk about changes in the surface of the Earth and how that's implicated within the carbon cycle, and also a measurement that we call albedo. You are going to want to make sure that you are accessing this Google Doc, which I am putting in the email, which will help you with your modeling activity. But also I gave you a note sheet on Tuesday that you're going to want to be using for the first part of this video, just to make sure that you feel good about some key elements for our lab on Friday. So we talked briefly about how in previous units related to soil and water that there are some really big changes going on Earth's surface. We have a lot of desertification occurring throughout sort of equatorial regions, where we're losing roughly the size of Bulgaria, which is right there, per year to arid soil, soil degradation, and aridity of the soil. So we're losing water. And in other huge parts of the world, we're losing a lot of our forests, which also have implications for soil health and also water reservoirs. And not only are these changes happening within physical surfaces, but also sea ice and glaciers are really on the decline in the past few decades. So our questions going forward for today and into Friday is thinking about how do all of these changes impact the carbon cycle, and B, how does the carbon cycle impact these changes or these cycles? So the first thing you need to know is that before human activity, the carbon cycle in terms of reservoirs and fluxes, reservoirs being stores of carbon and fluxes being the movement of carbon from one reservoir to the next, was pretty much neutral and even. Most carbon on planet Earth is inert and far from the atmosphere. We're really worried right now about carbon dioxide in the atmosphere. But when we look at gigatons, which are billions of tons of carbon, most of them are in the sediments of the ocean, fossils, and in the soil. Very little of it, only about 800 gigatons, are in the atmosphere. Now, natural reservoirs and fluxes that sort of impact the atmosphere would be plant and soil. And generally, photosynthesis takes out about 120 gigatons per year, while 60 are added to the atmosphere from plant respiration and animals and soil. While about 90 goes into the ocean for photosynthesis with phytoplankton, plants and animals in the ocean, and about 90 go back into the atmosphere. So the important thing to know is that before human activity, we were basically at net zero when it comes to carbon emissions that weren't extra. But currently humans are burning about 9 gigatons of fossil fuels or carbon dioxide per year, and we can only store about 3 extra of that 9 in photosynthesis and about 2 extra in the oceans. The other 4 remain in the atmosphere because there's nowhere else for it to go. There's no reservoir that can store that carbon dioxide, which is why we've had such a dramatic rise in CO2 levels in the past 200 years. The problem, though, is that with all of these problems related to soil degradation, deforestation, and also depletion of healthy water systems, these positive 2 and 3 probably aren't going to remain 3 and 2 for much longer. They're probably going to be reduced in the quantity that they're able to store because these reservoirs are going to be damaged and reduced and degraded. Now, the other thing that's really important to understand is really the surface of the Earth and how it interacts with energy and heat. And we call that albedo. Now, albedo is this measurement of how much solar radiation is initially reflected when the sun emits solar radiation to Earth's surfaces. Some portion of that is going to be instantly reflected like a mirror. And some surfaces are really good at reflecting solar radiation, like snow and clouds and ice, and some are really bad, like sand and forests and water. And these tend to absorb more energy per cubic meter of the Earth's surface. And what that means is when more energy is absorbed, the surface temperatures tend to rise, and when those surface temperatures rise, then we have changes in surface types because we're losing water, maybe the forests are being degraded, the soil is drying out, and then those higher surface temps result in more infrared radiation, heat, being re-released into the atmosphere. And while solar radiation bouncing off the surfaces of the Earth can escape out into space, this heat, this radiation is able to interact with greenhouse gases, causing us to have a warming of the atmosphere. This is the same thing as heat leaving your body when you're exercising and interacting with the insulation in your jacket. The heat can't escape fast enough. So, what are we going to be doing today? You, in this document, which is called Carbon Modeling Using NetLogo, are going to be making some changes to Earth's atmosphere using differences in albedo, CO2, and also clouds. Now, on the second page, there's some really good information about the parameters of the model and what it means for each of these different things, and also what is current Earth in terms of your initial setup. So what you're going to do is you're going to initially set up Earth in this game. So I'm going to go over to NetLogo and I'm going to go to Setup. The average albedo of Earth is about 0.3. We have 425 parts per million of CO2, and I'm going to add 5 clouds. And then I'm going to press go. And as the model goes on, you will notice that heat is absorbed when solar radiation hits the surface of the Earth. Clouds can deflect the sunlight out, and as temperatures rise, we will start to notice some infrared radiation leaving the high surface and being reflected back in by CO2. Now, within this document, I'm going to have you make 5 changes. It could be related to humans or changes with surfaces in the Earth. You're going to record what that change is. What are you going to do? You're going to record the tick number or the time, and then you're going to make a prediction. What do you think is going to happen? So my first change is that I'm going to pause at about 2,441 ticks, and I'm going to remove some CO2. I'm going to say that humans get rid of half of the CO2 by making better changes and being able to sequester CO2. And I'm going to predict that the temperature is going to go down. I'm going to let this run for a little bit. And then I'm going to, after I see a change, put the graph in here and analyze what happened. What were the changes that I saw? So let's go back. Notice that the temperature is still rising. So even though I removed half of the CO2, Earth's surface temperature is still pretty warm, so there's still radiation being emitted from the surface. And because there's still CO2, it's hard for me to get rid of it. But we have achieved a leveling off. There's not been any change in temperature. So you're going to do 5 of these observations where you make a change, you make a prediction, put it in the graph, and then analyze what you see in terms of what the model is showing. We will be doing another lab in class related to some physical models using CO2 and sunlight. So I hope this is a good entry point into understanding how the carbon cycle is dynamic and is interactive between the atmosphere and other cycles. See you soon.